Good morning, class. Let's start the day with a pop quiz. Get your pencils out, close your books. What's that? Not prepared? Feeling a bit nervous? Maybe even a hint of panic? Maybe by now you're breathing a bit heavily as your mind races to collect all your thoughts on our last lecture. You might even notice some trembling or tingling in your hands by now, right? Okay, you're off the hook. No pop quiz today. Instead, that was really a demonstration. In times of extreme stress or nervousness, it's a natural human tendency to breathe a bit too heavily and cause some of the other symptoms that I just described. You're probably familiar with this condition known as hyperventilating. Now, what might not be so familiar to you, though, is this. The symptoms associated with this condition all really come down to an imbalance in the acid-base chemistry of your own body. So obviously, controlling the pH of your blood is important. Far too important to leave up to chance. Fortunately for all of us, nature has provided a way to regulate the pH of solutions with relative ease. Enough at least that it takes something as terrifying as a pop quiz to throw them off balance. Over the next 2 lectures, we're going to get more familiar with acids and bases not just in isolation, but with acids and bases and how they interact in ways that can carry out many amazing functions, from moving mountains to regulating your blood chemistry. So let's get started. So we just spent the past 2 lectures painstakingly defining acids and bases and investigating how chemists characterize solutions of these very common and very important materials. But we have yet to carefully consider the reactions that can take place between acids and bases when solutions of the two come together. This is something that we simply can't ignore anymore. In natural systems, these reactions are just far too common and critical to the balance of nature to be left out of the discussion. Remember what acids and bases are. Our Bronsted-Lowry definition tells us that acids are proton donors and that bases are proton acceptors. So, what happens when we put an acid in the presence of a base? Well, of course, a chemical reaction can take place, one in which the acid releases a proton not to water, making a hydronium ion, which you might remember we usually write as a simple proton, but to base, forming that base's conjugate acid. Now, chemists call this very simple reaction a proton transfer reaction. So let's take a bit closer look at the simplest possible scenario, combining equal amounts of strong acid and strong base. Now, for this example, I'm going to use hydrochloric acid and sodium hydroxide as reagents. We already know that being a strong acid and a strong base, each one will dissociate completely into its constituent ions. But what happens when I combine one equivalent of each of these compounds? Well, we've brought 2 reagents together that are creating protons and hydroxide ions in large concentrations. Now, that should immediately set off some alarms for you, because we already have discussed Kw, the equilibrium constant for the autoionization of water. And we know that that's very, very small. It's 10 to the minus 14. High concentrations of protons and hydroxide ions simply can't exist. Right? They can't exist together. Now, if they did, everything I've just told you about equilibrium and autoionization of water has to be wrong. So let's consider what happens when these 2 reactions take place together. So let's start by just addressing the idea of a proton transfer reaction. So we know that HCl is a strong acid. Hydrochloric acid is an excellent source of hydrogen ions when it's dissolved in water. But now we also know that sodium hydroxide is a very strong base, which means that when we dissolve that in water, we get plenty of hydroxide ions. But what we haven't addressed yet is what happens when you mix the 2. Is this all that happens? We get just a collection of hydrogen ions, hydroxide ions, and salt? Well, not necessarily. Think carefully about what happens when a proton is mixed with a hydroxide ion in solution. Well, they have the potential to combine to make water, don't they? And we know that Kw for water is well in favor of that water forming. So if we were to mix reagents that are sources of hydrogen ions with other reagents that are sources of hydroxide ions, we expect those 2 to, for the most part, react with one another and form water, a neutral compound. So if we take this reaction here and sum the 2 together, Right? We can remove our hydroxide and protons that have reacted with one another, and the overall reaction that we see when you add hydrochloric acid to sodium hydroxide or vice versa is to make these products. We make a salt, in this case sodium chloride, and water, both of which are totally neutral. So adding lots of NaOH to lots and lots of HCl just creates lots and lots of salt water. It does not change pH dramatically. Now, what we're going to do is consider what happens when we incrementally add these to one another and how they affect the pH of a solution as this reaction goes on inside. So reacting equal amounts of strong acids and bases leads to a completely neutral solution of salt water. We call this kind of process a neutralization because the pH effects of both the acid and base are canceled out in the overall process. Now, this leads to a solution of water whose pH is governed simply by water's autoionization constant. Neutralization of acids and bases is not only a very common reaction, but one which was understood relatively early in the study of chemistry. Understanding this reaction can prove remarkably useful when trying to adjust the pH of a solution, specifically not just to a neutral pH of 7, but to any pH that we choose. So when a strong acid and a strong base come together in solution, we know they're going to react to neutralize one another. So let's think about what happens if we add a strong base to a strong acid incrementally. Well, here we are with our usual suspects here. We have hydrochloric acid as a strong acid. We have sodium hydroxide as a strong base. And we're going to consider what happens as we add solid sodium hydroxide to a solution of HCl. Now, the reason that we're doing this is it's going to simplify the mathematics here. If we were pouring one solution into another, we'd have to compensate for the dilution effects, which we know how to do because we've had our lecture already on solutions. But to keep this particular example as simple as possible, we'll be adding solid sodium hydroxide to the solution to maintain a constant volume. Now, let's think about the initial and final states of a solution of HCl as I incrementally add sodium hydroxide. Before any sodium hydroxide has been added, nothing's really happened. All I have is a 1 mole per liter solution of HCl. Let's say we're in a liter here. Nothing has happened whatsoever, so who's in charge of the pH here? Well, obviously the hydrochloric acid is. But let's add a little bit of sodium hydroxide, say a half a mole. Now that's not enough to completely neutralize the hydrochloric acid. It's enough to make about a half a mole of sodium chloride and a half a mole of water. But notice that in our final situation here, we've completely exhausted that sodium hydroxide and left behind some of the strong acid. So the unneutralized portion of the HCl is still in charge. Let's go a little bit farther. Let's add, let's say, 0.9 moles of sodium hydroxide. Well, now we're getting close, right? We're making lots of this neutral material that has no effect on pH. We've consumed all the sodium hydroxide, but we've still left behind just a little bit of that hydrochloric acid. HCl is still in charge. Now, we call these conditions pre-equivalence. At this point, I have not added a full equivalent of NaOH, so I have not yet completely reacted away all of my HCl. That's important to keep in mind, because the next step on our progression here is to add a little bit more sodium hydroxide, exactly 1 mole. Now let's take a look at what's happened. Now my 1 mole of sodium hydroxide has been completely reacted away, but so has my 1 mole of HCl. Because I've added a molar equivalent, I've completely neutralized the HCl. And what's left? Sodium and chloride ions, which have no effect on pH, and water, which is neutral. So what's driving the pH? Well, the water. It's all that's left to drive the pH. We call this the equivalence point. We reach equivalence when all of the acid and all of the base have been combined in an equimolar quantity. If I continue adding my strong base, I'm now in a situation where my 1.1 moles of sodium hydroxide leaves a little bit of leftover. So even though I've made some other stuff here, some salt and some water, what's left at the end of the reaction is a bit of strong base. And the strong base will drive the pH of this solution. That's what's going to dictate the behavior from a pH perspective. Adding more base, for example, 1.5 moles or 2 moles, just leads me to a situation in which I've got more and more of that base left over after it's finished neutralizing the HCl. We call this region post-equivalence. At this point, I've already completely neutralized hydrochloric acid, and adding more base will simply increase the basicity of the solution. So let's think for a moment about how this might look graphically if we calculate the pH values on all of these different conditions as I progressively add my sodium hydroxide. Well, in the pre-equivalence region of this plot, the HCl is in charge. So I can simply use the concentration of HCl, right, the negative log of that, to determine the pH values for these. At equivalence, the only thing in charge of the pH now is water. It's the only thing left. And we know that the pH of neutral water is 7.0. Progressing farther, now the sodium hydroxide's in charge. So I have to calculate pH via one of our tools from our previous lecture. In this case, I've chosen to calculate the pOH and subtract it from 14, giving me the pH values of 13, 13.7, and 14. So if I were to plot this information as equivalence of base added on the x-axis and the pH of my solution on the y-axis, I would see a plot that looks like this, starting at low pH, slowly working its way up until I approach equivalence, and then drastically changing pH very, very rapidly as the sodium hydroxide finishes neutralizing the HCl and ultimately takes over. So this curve shows us how progressively adding base to acid should change the pH of a solution. Not linearly, but logarithmically. Up here we have sodium hydroxide in charge because it's completely swamped out the HCl, whereas down here the acid itself is dictating the pH values. So by constantly adding or removing small quantities of strong acid and base, I could, in theory, maintain the pH of a system at a steady level while introducing nothing more than a bit of salt to the solution. But that's a lot of work and takes a lot of attention to constantly monitor pH and make small adjustments by adding more and more material to the system. It sounds like a really painful exercise to have to go through just to keep the pH of a solution steady. And it is. Fortunately, there's a far more simple solution. It involves a bit more complex chemistry, but it's a set it and forget it chemistry. One that gives us a break and lets equilibrium do the work for us. But first, we have some work to do. We have to think about how we're going to determine the concentration of a solution of weak acid as its conjugate base builds up in response to the rising pH. Unlike our earlier example of a strong acid, strong base neutralization reaction, which produced only water and neutral salt, this time neutralizing a weak acid produces a weak base, which has to be accounted for. Fortunately, we have a useful equation for this purpose. For this, we turn to the work of Lawrence Joseph Henderson and Karl Albert Hasselbalch. Henderson and Hasselbalch are most famous for their work surrounding the pH of blood and its effect on oxygen transport. Both men understood that hemoglobin itself was a vehicle for oxygen, but that the vehicle only worked properly when suitable blood plasma pH levels were maintained. And it's very easily derived using an expression that we're already familiar with, and that is Ka for a generic acid. Ka for any generic acid, of course, looks like this: protons times conjugate base concentration divided by the conjugate acid concentration. But let's rearrange this just a little bit. Let's divide through by proton concentration, and then take the negative log of both sides. Now, when we do this, notice that we have an expression here that we can expand to the negative log of Ka minus the negative log of proton concentration, and we'll keep the other side here just the same as it is. Now, these terms of the equation here and here should look awfully familiar to you. Yeah, that's right. They're the pKa and the pH. So this version of the sort of rearranged, manipulated acid dissociation constant gives us a relationship among the pKa of a compound, the pH of the solution that it is in, and the ratio of its conjugate acid and base concentrations. This gives us a great way to understand how a ratio or a combination of a conjugate acid and base will drive the pH behavior of a solution. Now, you may see the Henderson-Hasselbalch equation presented in a number of different ways. So I've worked it up here just in a few different arrangements to show you how it looks. The one that I derived previously is perfectly valid, but you may also see it in any one of these types of arrangements, all of which simply amount to shifting variables around for whatever purpose it is that we have. So Henderson-Hasselbalch can be used to calculate pKas or pHs or ratios of conjugate acids and bases, depending upon how we order it. The Henderson-Hasselbalch equation is indispensable in the fields of biology, medicine, and chemistry, in which the buffered pH of mixtures can mean the difference between success and failure, or even life and death. So now that we have a calculation that will allow us to determine pH values of solutions containing both weak acid and conjugate base, let's investigate that type of reaction. Now we're ready to do the same exercise that we did previously using strong acids and strong bases, but this time we're going to throw a little curveball in here. We're going to use a weak acid in the strong base and see how that affects the pH of the mixture as we progressively add more and more base. Let's use our classic weak acid here, acetic acid, and we're going to use our standard strong base as well, sodium hydroxide. But the key change here, notice, is that when these two react by proton transfer, we don't just get neutral species, we also get a conjugate base of acetic acid, which is going to change how that pH varies with the addition of sodium hydroxide. Let's take a look at how. When we start our addition of sodium hydroxide at the very beginning, of course, we haven't added any. And that means that our initial concentration of acetic acid for our calculation purposes will be 1 mole in that liter. And for now, we'll assume that there's nothing else in there that can drive the pH. However, as we add sodium hydroxide, things quickly change. Let's say that we've added 1/2 a mole of sodium hydroxide. At this point, that sodium hydroxide will have neutralized half of my acetic acid, leaving behind only 0.5 moles. And that will also create 0.5 moles of the acetate conjugate base. So unlike our strong acid situation here, we can't just assume that the only thing driving pH anymore is the acetic acid. We've got to be sure that we compensate for the fact that there's also conjugate base. We'll get to that in just a moment. Let's keep adding sodium hydroxide for now, though. Let's go with 0.9 moles. Now we have 0.1 moles of the acetic acid and 0.9 moles of its conjugate base, but no strong base left. So it's still going to be the equilibrium between the acetic acid and acetate that drives the pH of the solution. So these are our pre-equivalence situations. Now let's get to equivalence. When we add exactly 1 molar equivalent of sodium hydroxide, neutralizing all of the acetic acid, take a look at what we have. This is a bit different than last time, because in this case we do have something besides water that's going to be pushing the pH of the solution around. We've got a mole of the conjugate base, the acetate. We'll have to deal with that when the time comes to calculate pH. As we progress beyond equivalence, we reach a very familiar situation here, where the sodium hydroxide completely neutralizes the weak acid. And even though there is some acetate present here, the real driving force is going to be the leftover strong base, because strong acids and bases always win out in these kinds of situations. We can continue adding sodium hydroxide. All we're doing is increasing the amount that's left over when that neutralization reaction is complete. So this is our post-equivalent scenario. It looks an awful lot like our previous situation, doesn't it? Now let's think about the actual pHs of all of these different situations. Before we reach equivalence, we have to first think about, before adding anything, that we're just dealing with our acetic acid in solution. We would work this just like any other weak acid problem, getting us a pH value of 2.38 for a 1 mole per liter solution. But as we start adding the sodium hydroxide, we have yet to reach equivalence. We have not only that acetic acid, but we have some acetate here in each situation. And this is where the Henderson-Hasselbalch equation comes in. We can use the Henderson-Hasselbalch equation to determine the expected pH of a solution that's half acetate and half acetic acid, or that's 9 parts of acetate and 1 part acetic acid. We can use that ratio and the known pKa, 4.75, to get that number. So here with equal amounts, we calculate 4.75, whereas later in the process when we have unequal amounts, we have 9:1 ratio, we end up with a pH of 5.70. We continue to equivalence. We have to use the Kb of the acetate because it's the only thing left to drive the pH of the solution. And using that calculation, we get 9.38 for the pH. After we have finally completely swamped our acetic acid and we get some leftover sodium hydroxide, we can go back to calculating the pH as we did before. In this case, as I did before, I chose to calculate the pOH and then subtract that from 14 to get the pH itself. So how does our plot look different from our original? Well, let's take a look at that. If we put all of these values into our plot, you see a slight change in the shape, don't you? Down here, right around the pKa value, actually, it turns out, for acetic acid, we see a sort of a hump in the curve there, right? We see a leveling off that happens right at 4.75. And in this range, the solution appears to be more resistant to pH change. As I add more and more equivalents of base, very, very little change is observed in the pH until we get near equivalence and we completely consume all of the acetic acid, at which point sodium hydroxide takes over again. It's a very interesting feature, isn't it? Also, worth noting is that the equivalence point itself is no longer at neutrality. This is evidence for our conjugate base being in charge of the pH once all of the conjugate acid has been neutralized, but there's no leftover hydroxide to drive pH. So in this situation, it's the equilibrium that drives the pH behavior at low pHs, but it's the presence of excess sodium hydroxide that really drives it at the higher pHs. So we just saw how mixing strong acids and bases can lead to solutions of almost any pH we desire. Simply adding a small bit of strong acid or base to a solution of another alters the pH of that solution quite readily. But what about systems whose pH we don't want to alter? Is there some way that we can stabilize the pH of a solution and actually make it resistant to change? Now, just imagine that you're Søren Sørensen, working at Carlsberg Laboratory studying the effect of acidity on a variety of biological molecules. But the problem you're encountering is that proteins themselves consume and produce hydrogen ions when dissolved, throwing off the pH of the media that you carefully set at the beginning of your experiment. Without a constant pH, experimental control is ruined. Great. Now you have to sit at your reaction flask all day, closely monitoring the pH and adding a drop of acid here and a pinch of base there, just to maintain that simple but essential scientific control. This is exactly the kind of challenge that Sørensen faced. But Sørensen was no fool. He wasn't about to spend all of his time adding acids and bases dropwise to one another. His solution to the problem, no pun intended here, was not to hire an assistant to stand over his reactions all day with pipettes of acid and base. Instead, he mixed solutions not of strong acids and bases, but of weak acids and weak bases to achieve a media of the appropriate pH for his experiments. These mixtures of weak acids and bases have the remarkable ability to resist pH changes all on their own, because protons released into or removed from the solution by other means are balanced as the equilibrium between weak acid and base shifts. Essentially, the weak acids and bases in the system are adding and removing hydrogen ions here and there, all on their own. Molecular lab assistants. Genius. By mixing about equal amounts of a weak acid and its conjugate base, Sørensen could make solutions that fell into that plateau region from our reaction curve from earlier when we investigated acetic acid's behavior when neutralized. Now recall that the greatest resistance to pH change happens when an acid and conjugate base concentrations are about equal, which means at a pH equal to the pKa of the conjugate acid. So to select an appropriate buffer for a given pH, all we have to do is find a weak acid with a pKa near the pH of the experiment we want to conduct. Acetic acid acetate buffer would be ideal for buffering at a pH of 4.75, for example. Buffer solutions are an intrinsic part of chemistry and the world around us. For example, your blood is buffered partially by bicarbonate and carbonic acid. This mixture helps to keep your blood between pH 7.2 and 7.4. Anything outside of this narrow range is enough to cause medical distress, as the hemoglobin in your body fails to transport oxygen correctly. Now, carbonic acid has a pKa of 6.4. So, if your blood pH begins to drop precipitously, a condition known as acidosis, the bicarbonate-carbonate buffer system in your blood starts to kick in, resisting the drop in pH. A number of other buffers, including phosphates, all actually work in concert to help create a sophisticated system of buffers that protect you from drastic changes in the pH of your blood. So we've established that the pH of solutions can be dictated not only by creating strong acid and base solutions using the calculations from our last lecture, but also using neutralization reactions or even creating buffers. But how do we know the pH of a solution? All theory and calculations aside, is there a simple way to determine the pH of a solution experimentally to be sure we got it right? Indeed, there is. Sørensen pioneered the use of what are commonly called pH indicators. a class of compounds with two very distinct properties. First, they must absorb colored light very strongly. And second, they must undergo a proton transfer reaction of their own, which alters their color. Adolf von Baeyer, a prolific German chemist who had many interests, among them the synthesis of dyes like indigo, and another, a compound he discovered called phenolphthalein. Baeyer created this compound from the starting materials phenol and phthalic acid, hence its funny-sounding name. But phenolphthalein didn't really catch on as a dye compound because under neutral pH conditions it's actually colorless. But what Baeyer discovered, and what Sorensen summarily exploited, is that phenolphthalein is itself a weak Bronsted-Lowry acid with a pKa of about 8.2. And when phenolphthalein loses that acidic proton, it undergoes a chemical change that causes it to absorb green light, creating this attractive shade of fuchsia. Now, lots of compounds change color in response to changes in pH, but what makes phenolphthalein and other molecules like it very special is that they absorb visible light so strongly that only a minute amount of the compound is needed to give a solution strong color. So just a pinch of this indicator compound in a solution is enough to make the solution change color in response to pH without significantly changing the acid-base chemistry that's going on inside the solution. Phenolphthalein is not alone in this class of compound either. This is a good thing since characteristic color change of phenolphthalein only tells us when we pass the pH mark of 8.2. Some other very commonly encountered indicators include thymol blue, which changes from red to yellow at pH 1.2, then from yellow to blue at pH 8.0. Methyl orange goes from red to yellow at pH 3.1. Another indicator that you may have worked with yourself is phenol red. Phenol red undergoes a gradual shift from yellow to red over a pH range of 6.4 to 8.0. This makes it an ideal choice for testing of pool water for appropriate pH, since the ideal pH of pool water is directly in the middle of this transition. By adding just a drop of the test solution to a sample of water and comparing the color of the new solution to that on a reference card, one can quickly and easily verify the pH of their pool or hot tub to be sure that it's just right before jumping in. So in this lecture, we really mix things up when it comes to acids and bases, in a very literal sense. We started to think not just about how acids and bases affect the proton and hydroxyl ion concentrations in solutions, but also how acids and bases can react with one another when mixed. We considered the proton transfer reaction and how it causes acids and bases to neutralize one another. Then, we considered the effect of mixing weak acids and their conjugate bases. We saw how this can create buffer solutions which, depending on the relative acidity of the conjugate acid in the buffer system, can attenuate the pH change of solutions when more acid or base is added. Finally, we took a break from the theoretical work of predicting the behavior of acids and bases, and we engaged in the more practical question of how we can determine a solution's pH experimentally. Our solution to that issue came in the form of pH indicators, compounds whose very strong coloration changes or even disappears in a predictable way as the pH of a solution around them is altered. But there's even more acid-base chemistry to come. So far, we've limited our discussion to molecules that donate or accept a single hydrogen ion. Next time, we're going to expand our perspective by considering what happens when one molecule has the ability to do this with multiple hydrogen ions.